In this video, we're going to take a look at coding challenge named youngest ancestor, or also called youngest common ancestor. So what we need to construct is a function that accepts two nodes. So let's have an example that accepts node D and node C. And what we need to return is the youngest ancestor. So in this example, we return A, right? Because A is the common ancestor of D and C, right? So how would you solve this? Now, one way of solving this would be to have a scene variable. It's basically a set or a hash map. We take one node and go through each of the ancestors. So we go up, of course, we mark D as scene, then B, and go up, and A, right? After we're done, we go, we take a look at each ancestor from C until we find the common ancestor, right? So from this point, we look at scene, it's not there. We go up, okay, we see A, we just return A. So the time complexity for this solution would be linear, so of n, and it's the number of nodes inside a tree, and for space would also be of n, like this. So this would be one solution. A more optimal solution would be to not use additional space. What we would do is, from starting position of both nodes, we would calculate the depth, like so, calculate the difference, and advance the node with a bigger depth to match these nodes. So here we advance D to B, and now we can just advance both nodes at the same time, and we will eventually get to common ancestor, like so. So this solution would bring us to a space complexity that is better than O of n, so it's constant O of 1. Cool. So let's solve this in code. What we need to construct is few nodes. So let's have node A. We'll have, of course, let's construct these nodes as in this example here. So we have node P, node C, like this. Cool. Need to move node BC up here, so node 8 can have children B and C, and B and C also have children. So let's construct 3 more. So we have D, E, F. So D, E, and F, like so. So these guys are children for node B, D, E, and F. Node C has only G. Cool. G, like this. And another thing we need to do is this node needs to have an ancestor. So an ancestor A is just none, which will be the default value. So B, ancestor for B is A, and for C is also A, right? Next one. So for B, so we have D, B, we have D, E, F, has all these 3 children have the ancestor of B, and we have one child, G, as ancestor of C, like this. Now we need to construct class node, so let's do that. Node. we have value and we have children, which defaults to empty array like this. Okay. And the last thing, we have Ancestor, which defaults to none, like this. Cool. Hopefully this is wired all correctly. So A has B and C, this, B has D, E, F, so the children of B, and G is child of C. We wire these guys here, which looks good. Cool. Now we can finally solve this challenge. So let's just move this tree here, just for reference. So if we print youngest ancestor for, let's choose B and C, this should return us A. And if we have, let's say, D and G, this should also return us A. But if we have D and F, this should return us B. So we should have when we're finished with the youngest ancestor function, we should get results of A and B. Cool. So we have node 1 and node 2. So the first solution will use additional space, so the time will be in both cases of n, but space. For this solution would be of m, because we'll use set here. Okay, cool. Yeah, let's have scene variable, which is just a set. We'll have current variable that points to node 1. While cur, we can just say, okay, scene.add cur.value, and we can advance cur to be cur.ancestor, like this. Once we're done, we can reuse cur to point to node 2, while cur, and we check if cur.value in scene, we can return cur.value, like so. If not, we can just advance cur to the ancestor, like so. So if we run this, we should get back AAB, which we do, right? Okay, so this is one solution for this challenge. We can actually, do another one just for funsies, which it won't use additional space, right? In this case, we need to get a count for 1. So let's do let's have helper function depth will bring us depth of for node 1. Let's have for node 2 as well, like this. Let's have a diff function that's basically just count 1 minus count 2. Okay? We'll also have bigger the node with the bigger depth, which can start as node 1, smaller, which will be node 2. But if diff is less than 0, right? If this is positive, then count 1 is bigger than this guy, which is fine. This is correct. If not, let's first take care of diff. This is absolute diff, like this. And then we need to change bigger and smaller. So this becomes 2, this is 1. Cool. Okay. If the difference is more than 0, then we need to advance bigger to get the same level as smaller, right? So while if is greater than 0, diff -1 and bigger advances to the ancestor. It is. Here we're at the same level. We can say while bigger value is not the same as bigger smaller dot value, like this, we can advance both guys like this. Once we're done, we can just return bigger dot value like this. And hopefully, if this, oh no, we need to implement the depth before we can run this code. So let's do that. Depth node. We need to have a counter. So let's do this counter. Oh my god, cool. While node is not none, we advance counter and node ancestor like this. After we're done, we just return the counter like so. Cool. Let's just check if this looks good. So we're counting both depths, we're diffing both guys and setting bigger and smaller. If the diff is 0, we need to get the absolute difference between the two guys, just switch those nodes. We advance bigger, and after that we advance both guys. So it's good. Let's just run the code, and we get AAB, which is what we expect. Okay, so this is our challenge. We're done it. Yeah, I hope this helped, and see you guys next time. Bye.